Hello everyone, I am Dr. Lakhvinder Kaur, Associate Professor at Rungta College of Engineering and Technology, Bhilai. Today I am going to explain a topic signal propagation in optical fiber. I hope to share some valuable insights that will benefit you all, so let's get started. These are the outlines of the presentation which we are going to discuss in today's lecture. First is objective, then introduction, structure of an optical fiber, propagation of light through optical fibers, numerical aperture, pulse broadening through optical fiber, phase front analysis of propagation of light, analysis of and application of fiber optics, followed with the summary. Objectives: to get familiar with structure of an optical fiber, to understand propagation of light through optical fiber, to understand the concept of numerical aperture of optical fiber, to get the insight of pulse broadening phenomena in optical fibers, and to know about the phase front analysis of propagation of light through optical fibers. So, let us start with the introduction. Light is electromagnetic wave or made up of photons and has dual nature. It can be modeled in three different ways. First is ray model, wave model, and last one is quantum model. Such type of modeling is necessary because some of the phenomena are only explained using ray model. Some phenomena which are not explained by ray nature or model are well explained by wave model and quantum model. In this module, ray model is used to explain the propagation of light through optical fiber. Now, structure of an optical fiber. Constructionally, an optical fiber is a solid cylindrical glass rod called the core, through which light in the form of light or optical signal propagates. This is surrounded by another coaxial cylindrical structure made of glass of lower refractive index called the cladding. This basic arrangement that guides light over long distance is shown in the figure. Optical fiber has diameter of cladding is of the order of 125 nanometers and the diameter of core even smaller than that. Thus, it is very fine and brittle glass rod. In order to provide mechanical strength to this core cladding arrangement, other coaxial surrounding called the buffer coating and the jacketing layers are provided. They do not play any role in the propagation of light through the optical fiber, but are present solely for providing mechanical strength and support to the fiber. Now, the propagation of light through optical fiber. Propagation of light energy in the form of optical signal inside the core cladding arrangement and throughout the length of the fiber takes place by a phenomena called the total internal reflection of light. This phenomena occurs only when the refractive index of core is greater than the refractive index of cladding, and so the cladding is made from glass of lower refractive index. By multiple total internal reflections at the core cladding interface, the light propagates throughout the fiber over varying long distance with low attenuation. The essential requirements of the propagation of light through an optical fiber over long distance with minimum loss are discussed further. The figure shows a section of core of an optical fiber. If a ray of light is incident on the core of an optical fiber from the side, the ray of the light simply reflects out from the fiber on the other side. The ray shown in the figure demonstrates the situation. Launching light into optical fiber. Any light that enters the optical fiber from the side does not propagate along the fiber. Therefore, one has to launch the light through the tip of the fiber. That is, in order to guide light along the fiber, the light must be incident from the tip of the optical fiber. The red light is shown in figure. It also explains this situation. In other words, if the tip of the optical fiber is not exposed to light, no light will enter the filter as well as fiber. Although there may be ambient light, so long as the tip is protected, no light from the sides propagate along the fiber. Equivalently, if there was a propagation of light through the fiber, no light would emerge from the sides of the fiber. This characteristic of optical fiber imparts the advantage of information security to the optical fiber communication technology. Partial reflection of the core cladding interface does not suffice the propagation of light along the fiber over long distances. The reason is that at each reflection, a part of the optical energy launched into the optical fiber would be lost, and after a certain distance along the length of the fiber, the optical power would be negligibly low to the use. Thus, total internal reflection is an absolute necessity at each reflection for a sustained propagation of optical energy over long distance along the optical fiber. This precisely is the sole reason of launching light into the fiber at particular angles, so that light enters, propagates along the fiber by multiple total internal reflections at the core cladding interface. The ray model of light obeys the Snell's law. Now, the reflection of light at medium interface boundary. The figure depicts a situation of a typical refraction phenomena taking place at the interface of two optically different media having refractive indices n1 and n2. The angles are measured using Snell's law, and these are measured with respect to the normal to the media interface at the point of incidence. If n2 is greater than n1, then the angle of refraction is greater than the angle of incidence, and the refracted ray is said to have moved away from the normal. Similarly, if the angle of incidence theta 1 is increased further, the angle of refraction theta 2 also increases in accordance with the Snell's law, and at a particular angle of the incidence, the angle of refraction becomes 90 degree, and the refracted ray grays along the media interface. This angle of incidence is called the critical angle of incidence, represented by theta c of medium 2 with respect to the medium 1. This means the same optically denser medium may have different critical angles with respect to different optically rarer media. If theta 1 is increased beyond the critical angle, there exists no refracted ray, and the incident light ray is then reflected back into the same medium. This phenomena is called the total internal reflection of the light. The word total signifies that the entire light energy that was incident on the media interface is reflected back into the same medium. Total internal reflection obeys the law of reflection of light. This phenomena shows that light energy can be made to remain confined in the same medium when the angle of incidence is greater than the angle of reflection. There are two basic requirements for total internal reflection to occur. First, the medium from which light is incident must be optically denser than the medium to which it is incident. In figure, N2 is greater than N1. Similarly, second condition is the angle of incidence in the denser medium must be greater than the critical angle of the denser medium with respect to the rarer medium. Thus, we can say that light propagates inside an optical fiber because of multiple rays undergoing total internal reflections at the core cladding interface. In order to occur this, refractive index of the core glass must be greater than that of the cladding. This meets the first condition of a total internal reflection. All the light energy that is launched into the optical fiber through its tip does not get guided along the fiber. Only those light rays propagate through the fiber that are launched into the fiber at such an angle that the refracted ray inside the core of the optical fiber is incident on the core cladding interface at an angle greater than that of the critical angle of the core with respect to the cladding. Launching the light into the optical fiber. Figure shows how to launch light into an optical fiber. The light ray lies in a plane containing the axis of the optical fiber. Such plane which contains the fiber axis are called meridional planes, and consequently the rays lying in a meridianal plane are called meridianal ray. Infinite number of planes can pass through the axis of the fiber and an infinite number of planes. This proves that there are an infinite number of rays too, which are incident on the tip of the fiber, making an angle with the fiber axis as shown in the figure. These rays, after total internal reflection at the core cladding boundary, meet again at the axis of the optical fiber as shown in this figure, and consider is the plane of the paper which passes through the axis of the fiber and the incident ray, refracted ray, and the reflection rays lies on the plane of the paper. For the sake of the simplicity and clarity, only two rays are shown in the figure. However, in practice, there would be a number of rays that would be converge at the same point. One can classify these meridianal rays as bound and unbound ray. The ray that undergo total internal reflection inside the fiber core remain inside the core at all times along the propagation and are called as bound rays. The red ray in the figure is the bound ray. The ray that fails to undergo total internal reflection inside the core are lost into the cladding and are called unbound rays. The dotted green rays shown in the figure is an unbound rays. Since all the refracted rays meet at the same point, a region of high optical intensity is generated at that point. Due to multiple total internal reflection at the core cladding boundary, these rays meet repeatedly at the axis at regular intervals along the fiber. This causes multiple regions of maximum intensity along the axis of the fiber. Also, different set incident ray would have different angle of reflection at the core cladding boundary, and consequently have different points of maximum intensity along the fiber axis. Thus, axial region of fiber has more intensity and intensity gradually decreases towards the peripheral of the fiber core. Now, launching light using skew rays into optical fiber. As discussed earlier, one of the way of launching light into optical fiber is in axial direction, or another way of launching a light ray into an optical fiber is to launch light such that it does not lie in any other meridirectional plane. These rays are called skew rays. A pictorial representation of launching a skew ray is shown in the figure. Skew rays propagate without passing along the axis of the fiber. In fact, the skew rays go on spiraling around the axis of the optical fiber. The light energy carried by them is effectively confined to an annular region around the axis as shown in the figure. Therefore, intensity at the output of optical fiber due to skew rays will have minimum energy at the axis of the optical fiber, and it will gradually increases towards the periphery of the core. Hence, one can conclude that when light energy is launched into an optical fiber, there arises two possible energy distributions. One which has maximum intensity at the axis due to rays, and the other which has minimum intensity at the axis due to the skew rays. Thus, on the whole, there are two ways of launching light into an optical fiber. Light can be launched either as a ray or as a skew rays. Launching light into the optical fiber. One can simply analyze the propagation of light through optical fiber, assuming that light is launched as a ray into the optical fiber. The figure shows a cross section of an optical fiber with a core of refractive index N1 and a cladding of refractive index N2. The incident ray shown by a dotted line is the incident at an angle phi with the axis of the fiber. The refracted ray in the core shown by the dotted line 1 fails to incident on the core cladding interface at an angle greater or equal to the critical angle of the core with respect to the cladding, and hence refracts out of the core and is lost to the cladding. In other words, the angle of incidence of a refracted ray at the core cladding interface is in turn depends on the initial angle at which the incoming ray was launched into the fiber. If this launching angle is decreased, then the angle of incidence which the refracted ray makes at the core cladding incidence increases. If this increases in such as to exceed the critical angle of the core cladding interface, then total internal reflection of the refracted ray takes place and the light remains in the core and is guided along the fiber. The ray CO is launched into the fiber at such an angle alpha that its refracted ray is incident at the core cladding boundary at the critical angle theta c. If any light ray is launched at an angle more than alpha, then the refracted ray just refracts out to the cladding because the angle of incidence of its refracted ray at the core cladding interface is less than the critical angle. Thus, the angle alpha is indicative of the maximum possible angle of launching of a light ray that is expected by the fiber. Consequently, the angle alpha is called the angle of acceptance of the fiber core. Since the optical fiber is symmetrical about its axis, it is very clear that all the launched ray which make an angle alpha with the axis and form a sort of cone. This cone is called the acceptance cone of the fiber, as shown in the figure. Any launched ray that lies within the cone is accepted by the fiber, and the light of the ray is guided along the fiber by virtue of multiple total internal reflections as shown by the red ray in the figure. Next important parameter is numerical aperture of optical fiber. The figure below shows a cross section of an optical fiber having core of refractive index N1 and a cladding of refractive index N2 that surrounds the core glass. Consider a ray incident from medium 1 at the tip of the fiber making an angle alpha with the axis of the fiber. It is the acceptance angle of the fiber. The refracted ray for this incident ray is in the core, then in incident to the core cladding interface at the critical angle theta c of the core with respect to the cladding. The angle of refraction for critical angle of incidence is 90 degree, and the refracted ray thus gazes along the core cladding boundary, which is shown in the figure. According to Snell's law, the incident and the refracted ray lie in the same plane, which is the plane of the paper in this case. Applying Snell's law at the medium 1 core interface, we get n sin alpha is equals to n1 sin theta. The optical fiber is made of core and cladding. The presence of cladding is undesirable because it reduces the light accepting efficiency of the optical fiber. However, with a deep thought, one can realize that the prime concern behind prolonged research on optical fiber was not just to put light inside the optical fiber with the best efficiency, but also to propagate the light over long distance with the least attenuation. That means, if we have a source of optical signal and an optical fiber with the highest light accepting efficiency, but is incapable of propagating the accepted light, the optical fiber is of no use in spite of its high numerical aperture. Thus, judging the need of a cladding just on the basis of light launching efficiency would be highly inappropriate. In other words, light launching efficiency is just one of the key characteristic aspects of an optical fiber. There are other attributes too which have to be given importance while determining the quality of an optical fiber. One of such attribute of an optical fiber is its bandwidth. Larger bandwidths are desirable for high data rates of transmission. Next is pulse broadening in optical fiber. When optical fiber is used for transmission of information, light signal launched into it cannot be of continuous nature. For a carrier signal to carry information, one or more of its characteristic has to be altered in accordance to the data signal. In an optical fiber, light is launched in the form of optical pulses to transmit the required information. Light energy launched into the fiber may be considered to travel in the form of numerous rays in accordance to the ray model. These rays travel different paths inside the core of an optical fiber because different light rays are incident on the tip of the optical fiber at different angles within the acceptance cone itself. This causes different light rays in the acceptance cone to travel along different paths in the core of the optical fiber and accordingly take different time intervals to travel a given distance too, which leads to a phenomena of pulse broadening inside the core of the optical fiber. Thus, the pulse of light, which might originally be of width capital T seconds, now might be of T plus del T seconds inside the fiber core. The figure below depicts a pictorial description of how light pulse broadens inside the core of the fiber. Any incident ray that lies within the acceptance cone get guided inside the optical fiber by virtue of multiple total internal refractions. The amount of broadening is measured in the terms of the increase in the pulse time width and is denoted by del T. The value of del T is given by L n1 into n1 minus n2 divided by C n2, where del T is the pulse broadening, C is the velocity of light in free space, n1 is the refractive index of the core, similarly n2 is the refractive index of the cladding. The quantity L is the horizontal distance travelled before suffering the first total internal reflection by the refracted ray, which corresponds to the incident ray, incident at the acceptance angle as shown in the figure. The amount of pulse broadening is effectively the difference in time of travel between the ray travelling along the axis and the incident ray. This pulse broadening effect signifies that if a second pulse is now launched into the fiber within the time interval T plus del T, the two pulses will overlap and no identifiable data would be obtained at the output. Thus, for a given length L, there would be a corresponding value of del T, which would limit the rate at which light pulses can be launched into the optical fiber. In other words, it limits the rate at which data can be transmitted along the fiber. This indirectly limits the bandwidth available on the fiber. Thus, we can say that more the pulse broadening, lower the bandwidth. Hence, bandwidth is equals to 1 upon del T. Study of total internal reflection, phase front aspect. Let us now have a study of phenomena of total internal reflection at the core cladding interface on a backdrop of wave front of the incident and the reflected light plane of the light wave and are also called as phase fronts. They are perpendicular to the direction of propagation of the wave at every point. Any light ray launched within the acceptance cone will propagate along the fiber core by virtue of multiple total internal reflections at the core cladding interface. This figure shows the phenomena of total internal reflection of a ray of light at the core cladding boundary along the wave fronts of the incident and the reflected ray. The red and green colored dotted lines represents the wavefronts of the light ray which are perpendicular to their direction of propagation. The distance between a red and a green wavefront corresponds to a phase difference of 180 degree. The similar colored wavefronts have either 0 degree or 360 degree phase difference between them. Thus, when two similar colored wavefronts meet, they interface constructively, and dissimilar colored wavefronts interface destructively. This is evident from the interfaces pattern that's set up in the core as shown in the figure. In the core, the interface between the incident and reflected wave front constitutes a standing wave pattern of varying light intensity with discrete maxima and minima in a direction normal to the core cladding interface. If we refer to the electromagnetic wave theory of light, it shows that at total internal reflection, the light intensity inside the cladding is not completely zero. Instead, there exists some decaying field in the cladding which do not carry any power but supports the total internal reflection phenomena by satisfying the boundary condition at the core cladding interface. Phase front representation of propagation of light through optical fiber. With this backdrop knowledge about the propagation of light in an optical fiber, let us now look into certain finer aspects of such propagation and investigate the condition required for successful propagation of light in the fiber as shown below. Two parallel rays that are launched into the optical fiber and they propagate are shown in this figure. The dotted line represents the wavefront of the rays. The ray 2 is thus common to both the plane fronts. Thus, for a sustained constructive interface, the distance between these two phase fronts must be multiple of 2 pi. In other words, it can be said that the phase difference between the phase change undergone by the ray 1 in travelling distance S1 and the ray 2 in travelling distance S2 must be 0 or integral multiple of 2 pi. The light propagates through optical fiber by the phenomena known as total internal reflection. Only those rays which satisfy the condition of total internal reflection, that is, the angle of incidence less than critical angle, can travel through optical fiber. Due to this, optical fiber is considered to have certain cone of acceptance known as numerical aperture. It depends on the refractive indices of core and cladding and core radius of optical fiber. As number of rays travel through optical fiber over the length, they may not meet at the same point at the other end of the fiber. This leads to the pulse broadening of the light wave launched into the optical fiber. Phase front analysis of propagation of light through optical fiber is also explained into detail. Generation of wavefront due to number of rays travelling through optical fiber leads to formation of interference pattern. This causes generation of maximas and minimas along the axis of the fiber. Thank you.